by Martin Popel through machine translation Zoo. So I'm looking forward to what we will see and what we will hear. Please take the floor.
Okay, good afternoon, everyone. I hope you like zebras and horses, lions, so we will see some nice, stupid pictures and so on. Well, this will be a part of, I will present part of my PhD research. Probably most of you know that the topic of my PhD is TectoMT system, which is a machine translation system with transfer over tectogrammatical layers. So it's linguistically motivated, and most of my previous talk were focused on this aspect of this, let's say, superiority of linguistically motivated deep syntactic transfer over surfaced phrase-based systems. However, in this talk, I would like to focus on other aspects of this research. So first, I will say something about machine translation. I will do some introduction, the taxonomy of the beasts which live in this world of MT. And I will also show you some newly discovered hybrid systems. Actually, the newest one was just created or discovered this Friday and submitted to WMT competition. And it's also a work of my colleagues, I will say. And then let's say, the meat of the main flesh will be machine learning. It's needed for, if I want to do some advance, I want to somehow combine those two fields or use knowledge from both. So I will focus on two approaches or fields in machine learning, namely online learning with structured perceptron and guided learning. And finally, I will show what I'm now working on. So I will move back to machine translation and show how to apply the machine learning, namely I will show a novel decoding algorithm for MT and also closely related guided learning approach. So let's start. Probably most of you know phrase-based system. I will just quickly review it, how it works. So the probably most popular system is Moses, open source, and there are two parts. First, you must train the system using some parallel data and monolingual data from the target language, and then the decoding comes. So in the training phase, you use some word aligner usually, and you should have in mind that it's just approximation or heuristic. Let's say it's not a monolithic system. It's several heuristics are done for the symmetrization. First you align, let's say, English with Czech and then Czech with English, but you want the alignments symmetric. So, well, then comes phrase extraction, where you extract all n-grams, or I mean phrases, which are consistent with the alignment. It means that no alignment links cross the phrase pair. And finally, you tune the parameters in the log linear model. Actually, usually it's called log linear model, but it's only a linear model since no normalization is done there. So I just a few weeks ago discovered that it's probably a wrong name for this, but everyone uses it. Okay, and in a decoding phase, you look into your dictionary, I mean the phrase table, and for the input sentence, you find all rules which match the sentence. It means that you find all n-grams, which you can cover, the source part of the rule can cover it. So there are multiple derivations how you may get one translation. You can select different segmentation on phrases, but those different segmentation may lead to the same translation. So it should be correct from the statistical point of view to select the to compute the score of the translation as a summation of all derivations which could produce this translation. But this is not usually done. It's too computationally, it would take too long. So usually only the derivation with maximum score is search, and even this search cannot be done exactly, and it's approximated using beam search. So you say, let's say you will have 100 hypotheses in each stack, and it may happen that a hypothesis didn't fit into the first 100, although if we continue, it would get the best score. So this is a kind of search error. Okay, so this was Moses, and now something completely different, the TectoMT system. It's based, as I already said, on tectogrammatical analysis. So we have a Czech English parallel corpus, Czech, and it is analyzed both the Czech and English side. It's analyzed up to tectogrammatical layer. Then we align, but not words, but the tectogrammatical nodes. And actually we can also use Giza and project the alignment upwards. And here comes from the point of view of this talk, it's the biggest distinction that the current TectoMT system translates isomorphically. It means one node to one node. In the core transfer step, it is not possible to translate one word, the content word to two words. We have some blocks which are applied before the main transfer or afterwards, and therefore it is possible, for example, to add the word year, to add the word year when we translate into Czech, but the main transfer cannot do it. On the other hand, it is not such a big disadvantage as if the transfer was done on a lower layer. And we learn one maximum entropy model for each lemma. Well, I will show an example. So we have a source sentence. He agreed with the unions to cut all overtime. This is simplified tectogrammatical tree. Actually, only lemmas and phonemes are shown here. Phonemes don't belong to the theoretical tectogrammatical layer. They are just a technical mean, or we find it useful in translation. So you can see that here is the preposition with. And, I don't have the Czech phonemes on the picture. But the point is here, we want to translate the node cut, and all the blue attributes are used as features in the model. So these are the possible equivalents of the Czech translation of cut, chop, saw, trim, shorten, and some of those features may be useful to assign the probabilities correctly and choose the best translation. So in this case, it was dohodl se s odbory na zrušení všech přesčasů. The distinction is that in TectoMT we have just one segmentation. Actually, each node is one segment which is translated not independently on the rest of the sentence. Actually, the local neighborhood in the tree is used for the features. But we don't try currently to translate 2 nodes at once, or translate 3 nodes into 2 nodes, and so on, which would allow non-isomorphic transfer. So actually, this was the first motivation. Some portion of errors is caused because of this assumption of isomorphism, so I wanted to find a solution for this which would allow to train such bigger segments, and in the tree I call it treelets, which is a connected subgraph of a tree. So, actually, the maximum entropy model suggests as a translation model, translation of lemmas and phonemes, and then we do a variant of hidden Markov model, Viterbi algorithm, but not on sequences, but on trees, and we find globally optimum. So we have no search errors in current TectoMT, which is somehow unbelievable for a phrase-based system, but it's thanks to the fact that the features are local. Actually, the features on the target side, where instead of usual Ngram language model, we use target language tree model. So it predicts the probability of a node, I mean of its label, given its parent node. So we don't look on siblings. Actually, the dependencies on children get there through the Viterbi search. But with such restricted features, it is possible to do globally optimum search. Well, we restrict the number of translation options, let's say to 7, but even if we increase the number, the scores don't increase. So it's not a search error, but a modeling error which we face. So now here is the taxonomy. So here are several criteria which you can, or questions which you can ask when you find a new system, new MT system, new animal. So statistical MT started, well, actually it was before, but maybe the most popular paper is 1993 in IBM models for word alignment. So it was based on translating one word to one word. Actually, it was possible to translate one word to more words, but the base translation unit was word. No linguistic analysis was done. Actually, there were done some, for example, some phrases were in the pre-processing step merged together, but not in a general way. Well, so only one segmentation was possible. Each word was a segment, so also the one possible segmentation was used in decoding, and the modeling of the translation model used the base translation unit, the probability of target translation unit given source. Actually, you can have also the opposite probability, source given target. But what I want to point out that no other context was used here except of language model, which was used in the decoding and reordering model. But the very translation model doesn't look on other parts of a sentence, or not even on previous sentences. So, phrase-based models, now the most popular system is Moses, therefore it was Pharaoh in 2003. So instead of one word, it's a sequence of subsequent words, so phrase. Still we don't do any linguistic analysis, but we extract more segmentations from the training parallel corpus, and we consider them, but finally we use just the one segmentation, I mean the derivation with the maximum score we were able to find. So if you delete all other rules from the phrase table which were not used in this derivation, and you apply the algorithm again on the same sentence, you will get the same result. So, yes. Hierarchical phrase-based systems, you can consider it as a tree, but the tree is not linguistically motivated. It's more a phrase with gaps, so we consider all possible trees, binary trees, constituency trees where the non-terminals in the classical approach have just one possible label, so it's really just a phrase where you allow gaps inside which can be where another phrase can be substituted. And the same characteristics as for the phrase-based system. This sample of systems is not representative. I just selected some of my favorites. So Quirk and Menezes from Microsoft Research in 2006 developed an MT system which used dependency trees. I think it was one of the first system which exploited dependency trees and was able to show some improvement over phrase-based system or the state of the art at that time, at 2006. However, they just parsed the source sentence and the source side of the parallel corpus and projected the dependencies to the target side. So they didn't need a parser for target side. So you can say it's a tree to string transfer, although you have the target trees there, but their dependencies, the topology of the target trees is just copied from the source. And what's interesting here, the base translation unit, or they call it minimal translation unit, it's basically one or more nodes which were not able to align, which were the minimal translation unit considering the alignment, but they also look on the neighboring treelets or the neighboring base translation unit. So in a tree, on the parent treelet and children treelets, they are considered in the probabilistic model. And also another favorite system of mine, TectoMT, it finally uses deep syntactic, namely tectogrammatical analysis. The base unit is tectogrammatical node, and we have just one segmentation. Each node is one segment, but we use neighboring nodes, as I showed on the previous slide, as context features in the maximum entropy model. So, and just to show that it is possible to use more segmentations in the output translation, or that the probability of the translation is done as a summation over more derivations. So several scientists tried to this. Maybe the most, or one of the latest is PhD thesis of Abhishek Arun, and they used Bayesian inference techniques like Gibbs sampling, or actually here it was even something better, they say. So it is not possible to exactly find the huge number of derivations which lead to one translation, or to all possible translations which we want to score, but using sampling we can approximate this sum. So it's more sound from the theoretical point of view. However, the computation time if I remember correctly, maybe it was a different paper, but it was 3 hours for one sentence. So, but they are improving very quickly. Well, if you have any questions anytime, feel free to ask and interrupt me. So, and now let's look on some hybrid systems. So this slide is just the original TectoMT, where the analysis and transfer and synthesis phases are shown. These yellow parts are statistical blocks or components. These blue are rule-based. And actually the most important is the transfer phase, where we use the maximum entropy model or dictionary and hidden Markov tree models. And I had an idea to use Moses for this part. So substitute the maximum entropy model and hidden Markov models with Moses. So I asked Aleš Tamchina for help, because I cannot do so many experiments and I'm not so experienced in running Moses. And we tried it, but it looked kind of promising, but not so much. So I would continue in this research, but it is open for anyone. So just to the idea is that I linearize the tectogrammatical trees. I just forget the topology and I take it as a sequence of lemmas and phonemes. And actually these are, you can take an interleave sentence where you would have one lemma, one phoneme, one lemma, one phoneme, but there is another option to use 2 factors and factored translation setup in Moses. So we use this approach. And do I have a slide? Yes, so it's a kind of hybrid. And the final synthesis was the same, the original TectoMT synthesis, and the dependencies were projected there from the source side.
Characterize your results?
Oh yes, results. You shouldn't. I don't have any results in this talk, so you can enjoy the pictures of animals instead. Yes. So another hybrid system is called PhraseFix. Actually, the motivation for the name is from the DepFix system by Rudolf Rossa. But this is that first we run TectoMT system, and then we post-edit the output of TectoMT using Moses. So it means that the Moses is trained on a parallel corpus, where one language is a pseudo-check. It's the check as TectoMT outputs it, and the other language is the correct check reference translation. So the whole check corpus was translated with TectoMT, and Moses was trained on the output. And this helps from the point of blue score. It improved, but as we expected, the Moses has the merit optimization and can do very well on blue score, although the human judge quality doesn't need to correlate with this. So we tried, and we hope that the TectoMT output will have some qualities, like maybe some grammatical coherence and so on, and we didn't want to destroy those qualities. So our aim was to find a way how to post-edit it, but only in such cases where the Moses system is really confident that error was done here. If the Moses in this phrase 100 times was output like this in the TectoMT output, but in the reference it was like this, and just 2 times it was translated differently, then it can be really sure that it should change it. But when it is not so sure, the advantage of this approach is that it can leave it untranslated, I mean unchanged. But what looks as an advantage on the first side, and actually you don't need to consider reordering models so much, we expect that the TectoMT gets the word order almost correctly, and at least in Czech we don't care so much. Actually, it can be, the sentence can be understood even with slightly different word order. If you leave the English one, we are not on a such high level to consider topic focus articulation and so on, of course. So, here are some ideas. These we somehow tried actually. Petra Galuščáková did the experiments. I did a prototype half a year ago, but now for WMT, the system was already submitted this Friday, so the experiments were done by Petra. So one just very simple idea was to filter the phrase table, just the phrases with low score, probably the forward probability phrase, just delete it. Hard constraint, just delete it from the phrase table. Unfortunately, this led to, when the pruning was screwed, when I looked at the phrase table, I said, oh, these are really good substitutions. These are really errors of TectoMT. So when I was satisfied with the quality of the phrase table, then the quality of the phrase fix was really low. And the problems are hard to explain now, but it may have to done with out of vocabulary words and the language model and so on. We are not sure exactly how to deal with this. So another idea was not to delete those rules completely, just to give a hint to the Moses that such rules are not confident enough, so add another feature to the merit optimization. So, and we hope that it will learn that the really sure substitutions should be used, but other not. Well, I don't know. Maybe Petra can tell you more afterwards whether this really helped or not. I'm not sure what was the last result. It changed all the time, but we also decided we can improve the alignment. The Giza aligner expects 2 completely different languages, and it takes each word as an atomic unit. Well, actually, it computes sometimes Brown clusters, and can do stems, but it doesn't expect that it's actually the same language. It's actually monolingual alignment. And we would like to promote that the same word should be aligned with the same word. So, well, the approach we choose is not a good one. Zdeněk shouldn't hear me that we have did it, but we just add identity parallel corpus to the TectoMT reference corpus, and we hope that it will somehow, that the Giza will realize that it can align the same word to the same word. And, a different idea was to boost the phrase table with identity, so also not only the alignment, but also the phrase-based system, the Moses learns that it can leave the phrase untranslated, and it's okay. So, the future work is, there are many ideas I have, so we can use also the English source sentences in this approach, so then it's not just post-editing, but joint translation and post-editing, which is similar to so-called multi-source translation, where, for example, you have sentences in Spanish and Italian, and you want to translate it to English, so you can translates both sentences jointly. And you had a parallel corpus also for the Italian, Spanish, and Italian English and Spanish English. So there are some techniques for this, but we haven't tried this. We can also project only content words from the English and align it to the Czech sentence. Actually, TectoMT already knows how it was produced, so we don't need to run any aligner, just program in a TectoMT so it outputs the alignment. And it can be another feature, either another factor or somehow differently. It can be implemented in the Moses system. And with factor translation, there is a special algorithmic goal that when we have, for example, lemmas and part of speech text, then the current factor translation chooses a segmentation, but in each segmentation, each segment of lemmas must have the same number of lemmas as text. Is it clear? I don't have a picture here, but if we have lemmas and part of speech text, so it is not possible, for example, to have such phrases currently. There was some effort by the author of Moses, am I right? But it was too hard algorithmically to program it. So this should mean that PhraseFix is actually existing animal. This is Okapi, it's real. But the future work, well, who knows? So, and even more hybrid systems. So this is not mine work, but DepFix is by Rudolf Rossa. It's the opposite of PhraseFix. It's a rule-based or syntactically or linguistically motivated post-editation of statistical machine translation. So first Moses or another system like Google translates a sentence, and then DepFix analyze the sentence. Actually, it needs a robust parsing since there are errors in the output, and also it exploits the source sentence, and there are manually written rules mostly to improve agreement and other grammatical categories. Another idea by Ondřej Bojar is to use TectoMT to generate additional training data for Moses. So we translated English monolingual news, huge amounts of monolingual text, into Czech, and presented this to Moses as another parallel corpus, of course in addition to the real parallel corpus Czech. And this is one setup. Another setup is just to translate the development sets from the WMT competitions, which are more similar to the task we want to do. Namely, we can also translate the test set. So to enrich the phrase table for such translations which are probable to be needed in the task we are going to do. It's not cheating, since we don't look on the reference translations of the test set. We just translate it using TectoMT, and this output is then used in Moses. So, actually, those two animals were kind of tame and mild, but this one, it's really chimera. It's a hybrid of hybrids. So this Friday, Ondřej had idea to combine add to train with DepFix. So it's actually TectoMT combined with Moses, combined with DepFix, and the goal is to beat Google this year, finally, without using Google. DepFix already has beaten Google last year using Google output. So this is kind of harder task. Okay, so we will see. Actually, you can play the role of Bellerophon, the guy who killed Chimera with Pegasus. So you can take part in the annotation process of WMT. It should start, I think, in 1 month or in a few weeks. So now let's completely switch. Or do you have some questions to the previous part? Okay, so I will switch to machine learning, and I will start with perceptron, which is an algorithm which probably most of you know, but then I will gradually add new things. Okay, so the advantage of online learning, and perceptron is a special case of online learning, is that it's really simple. This is the whole algorithm. So you can program it in a few minutes. Actually, the idea is that first you have some parameters called weights of the model. You initialize, let's say, all to 0 or some small random value. And then you get an instance or observations, and it's a supervised task, so you want to find a label for this observation, but the idea is that you get just one label, one observation at a time. So here I don't use any subscript, just X is the observation, and Y for simplicity, I use gold as the correct answer, the correct label. But the ordering is first you get this instance, and I just consider this as a vector of features to make the notation simpler. So you get new observation, you do the prediction, and this is the predicted label. After that, you get from the outside world the correct label, and you update the weight. So if you did an error, you somehow update the weight so you are less likely to do the same error next time. That's the general approach. And after someone decides that it was enough data, or you can output the weight vector, actually online algorithms can be used for really online problems such as weather forecast, where every day you want to predict the tomorrow's weather, or I don't know, few days in advance, and soon afterwards you get the correct answer. And the advantage of online learning is that it can adapt. If winter comes, then actually all the gold labels will be very cold temperatures, so the algorithm will automatically adapt to this. However, in NLP and also other areas, we don't need this online approach just for it. We have all the data in advance, so we could apply also an opposite of online algorithm, which is a batch, when you train on all data together. However, it has other advantages. One of them, as I said, is that it's simple to implement, and also sometimes it can solve problems which could not be so easily solved, or it's competitive with batch training algorithms. So if you have heard that perceptron, it was in 1960s and it cannot solve the XOR problem, so let's forget about it. Well, the state-of-the-art algorithms are actually based on perceptron, just modifications. Okay, so I won't go into the details. This shouldn't be a lecture. There are some practical issues, like that if you really have the data in advance, you should probably do more iterations over the data, so put the same data again there. So, and finally, output not the last weight vector, but the average of all vectors which were there. So this is called average perceptron. There are other tricks possible, but let's have a bit of theory. So definitions. the online algorithm is said to be conservative if, when there is no error, so when the predicted label was the same as the gold label, then no update happened. So, you probably discovered that how to implement this procedure prediction and this procedure update, that's the most important. Such updates where this constraint holds are called conservative. There is a related definition, passive, which is similar to this, but sometimes, although you get the predicted label the same as the gold label, but you computed a score, and the score was very near to another wrongly labeled example. So the margin between the correct label and wrong label was too small. You may decide do the update even in that case, rather to make the margin larger, to separate the correct labels from the wrong labels. So this would be called passive, when this is allowed, but it's not allowed to update when there is no loss. Well, I will give the definitions later. The algorithm is said to be aggressive when after the update, if the instance, the same instance, would be predicted, it would be classified correctly. So with the updated weights, now we would get the gold. So we did the update so large, so it predicts the current observation correctly. Okay, so in binary classification, the labels y's can have only two values, 0 or 1. So the prediction is a dot product of weights and of the feature vector. And this notation, this bracket is called Iverson bracket. Just it's if the condition holds, it's 1, otherwise it's 0, just to make the notation shorter. And so you can think of the dot product as a similarity score. So if the weight is similar enough to the current observation, so the dot product is higher than 0, then it will output label 1, otherwise label 0. And the update is simply, this is some constant called learning rate, usually, or in the original Perceptron it was just 1. And this is, if error happened, then this is either 1 minus 0 or 0 minus 1. So this just means that we either add or subtract the features from the weight vector. So very simple. Now, if you have a multi-class classification problem where there are more labels from 3 or up to 20, let's say, or maybe 50, this is the general form or multi-class perceptron, where you don't take features just from the observation, but you have a feature function which also considers the label. And as a special case, if you have low number of classes, you can just for each class repeat the feature. So you can think of it as one feature vector for each class. But you can concatenate those feature vectors into one long feature vector. So this feature vector has a dimension number of the original features times number of classes. However, in a general case, you don't need to restrict the features in such a way, and you can design feature which looks on two labels. And so this feature, for example, says if the current label is proper noun or proper noun in plural, and the current word is capitalized, then this feature is 1, otherwise it's 0. And you could have two features, one which would be a conjunction of proper noun and capitalized, another proper noun in plural and capitalized, but you would need to have two weights for this. And sometimes if you believe that there should be just one weight for this, then the algorithm may be more robust if you design such a feature. And you maybe can look inside if the label has a structure and so on. So this is another machine learning task called structured prediction, where you can think of it as a multi-class classification problem, but the difference is that the number of possible labels, Ys, is really huge, exponential, like billions or even more. Sometimes you don't know in advance what the features will be in structured predictions problem. Well, to have a better idea, what does it mean? So the Y, now I use bold font as you can think of it as a vector, and it can be a graph, dependency graph. So this is for dependency parsing. The input, X, is one sentence, and the output is the whole graph. I mean, dependency tree, or for sequences, for part of speech tagging, input is a sequence and output is a sequence of text. There is the number of text is the same as the number of words, similarly for, well. So one property which usually holds, so this problem is solvable, is that you can somehow decompose the big problem, like the classification of the whole sentence, into some sub-problems. So in part of speech tagging, you can take individual parts of the sentence and then put it together to get the score of the whole sequence of text. So usually how the factorization in decoding can be done depends on what features have you defined. So you have, I call it local features, and also in literature sometimes you may find it, and I use small letter f in contrast to capital F. So the small f can look on the whole sequence of X, on all words which were on the input, but only on some labels. Usually it's that we only look into the history, and in first order Markov model we are allowed only to look on the nearest previous label. In second order on the two previous labels, and so on. And this allows us to use efficient algorithms for decoding and also for training, like Viterbi decoding and forward, backward, and so on. You can have a feature, here is a conjunction as it was before, and this bracket means that the value of this feature is either 0 or 1. The similar feature here for the whole sentence can be defined using this formula, and then it's just a sum of the local features. So this is the number of capitalized words with which were proper nouns, either in singular or plural. And you can also have a feature which looks on the whole input sentence. So, for example, this means that there were less than 7 words. So this feature is a number of NNP followed by NNP, but if the sentence was longer than 6 words, then the value of this feature will be 0. Well, I don't say this is a useful feature, just an example how you can define features. And you can also define global features which cannot be decomposed into local features. However, in that case, you are not able to use those efficient algorithms, so you must have another approach how to solve the problem, for example, using sampling and Bayesian inference. Okay. So, even more important than the features are the approaches or definition in textbooks. When you hear structured prediction, some people prefer to think of it in this local approach, and some prefer this global approach. So the local approach is in online learning in particular, that you solve the subtask. So for example, take each word at time using the outputs from the previous decision, it means the previous text, and you can use whatever classifier, classical classifier you have, in the case that this non-bold Y's, I mean the individual texts, are normal multi-class problems. So you have 42 texts in Pentry Bank or 100 texts, it's doable. You can define, you know which 42 texts those are, you can define the features in advance and store it somewhere. So this is the case of the famous structured perceptron by Collins. He didn't call it structured, but afterwards it's called structured because it's a perceptron used for structured prediction. And the prediction is just a score. This is the score of the local features, but here, for example, in the structured perceptron, we look on the previous tag. So this way the structure gets inside. On the other hand, you can think of it in a global approach, where first you somehow generate the n-best list of outputs for the input sequence X. So let's say 1,000 sequences of text or 1,000 parse trees. And then you compute global features on each member of the n-best list, and you can think of it that you do re-ranking of the n-best list. Using the features, you do one update on the whole n-best list. So the difference is in online learning, here you do update of weights after each sub-problem, here only when the whole, let's say, sentence is solved. And you can use, for example, mirror algorithm, where you try to aggressively separate the correct labels from the incorrect labels so that the margin between them is larger than the loss you would suffer if you get the incorrect label sequence. And, well, I will get to this later. Sorry for the unclear sentence. Just here is the formula. So it looks similarly, but now you select the label or hypothesis with the maximum score of the global features. So let's have some more definitions, theoretical, but you can see there are only a few more slides left. So hopefully afterwards there will be some pictures of animals. And the score is just a short notation for the dot product of weights and vectors. You define the margin of a label as a difference between the score of the correct label and the label you are judging. Actually, sometimes you can see that also the gold label is a parameter for the margin, but I just try to simplify it. So usually you think of it that the margin, when it's positive, it means there is no error, and the absolute value of the margin is the confidence, how much you are confident with this label. So you usually want to have the margin as large as possible, or, I don't want to go into details, but you can define loss, and sometimes this particular kind of loss, it's called hinge loss, where you want the margin to be at least 1, and actually this is in the case where the labels are either correct or not correct. So the cost you would pay for predicting incorrect label is just 1 or 0 if you get the correct one, nothing between. So therefore this is the cost, and you want the margin to be larger than this cost, and the loss must be always positive or 0, and it is 0 when no error was done. So now let's review what was on previous slide in online prediction. This is the formula for the prediction, and this is formula for the update. You just take the difference between the feature vectors of the gold correct label and the predicted label, and you add it to the weight vector. It means that you promote or boost the gold label and penalize the incorrect label. But if it wasn't really incorrect, I mean when the loss would be 0, then for example here, in this case, the alpha constant would be also 0, so no update would be done here. So in the original perceptron, the alpha is a constant, either 1 or any positive constant, but there is a set of so-called passive-aggressive algorithms by Kramer and Singer, and the aim of the passive-aggressive update is well, to be aggressive. So this, if you do it, the update computed in this way, this is the norm of the difference, then it is granted that now the label would be predicted correctly, or the observation would get the gold label. And there are two variants which should be somehow robust to noise in the data. So maybe you have one instance where the label was not correctly annotated, or it's some extreme, and it would mean that just if you want to do aggressive update also on this label, you would change the weight vector to a completely different value than was before. And it may take many other iterations to get back. So here you just say, okay, I don't want the learning rate, the constant alpha, to be higher than C, at most C. And it has some nice theoretical properties. Well, if you're interested, you can read the paper. I just wanted to show that this is easy to implement, and still the whole algorithm, well, it's not here, it's easy, and there are some mathematical formulas and derivations behind, but the result is such simple. Okay, and I already started describing this before. So cost, by definition, is some extrinsic error metric. So it must be always non-negative, and you can think of it as if the cost is between 0 and 1, then you can think of it as a 1 minus similarity of the predicted label and the gold label. So in the simplest case, you have just 0, 1 cost. But you can, for part of speech tagging, you can say, well, proper noun in plural and singular, I don't care about this. It's a minor error. It's not like predicting verb instead of noun. So you can put different cost for different errors. Well, this maybe is not so sensible, but if you are going to, if it's the global approach and the Y is the whole sequence, then it's quite natural that the cost will be number of errors or percentage of errors, so percentage of incorrectly labeled words in the sequence. And in that case, you have much more possibilities how to do the update. So first, you can redefine the hinge loss as here. So you take the cost minus the margin, and it cannot be negative. And before we had here, we want to boost the correct gold label and penalize the predicted label. Let's make it more general, and instead of gold and predicted, let's call it hope label or hope hypothesis and fear hypothesis. The naming is somehow confusing. Someone used the hope and fear only for a particular special case of the hope and fear as I define it here, but I like the term, so I use it. So what we had before, if you define hope like this, that it's the hypothesis, well, this is minus cost, so it means that we are looking for a hypothesis with the minimum cost, so with the minimal number of errors. So if you can iterate over the gold hypothesis, this would be 0. So you would get this minimum cost hope will be the same as the gold. But it's possible that your algorithm, like the part which generates the embeds list, is not able to generate the reference. So then it may not be useful, or in machine translation it's even not possible in phrase-based machine translation to use the reference translation, the gold, as a hope which you want to boost. I will go to it, back to it later. And actually, this definition of fear is that the hypothesis with a maximum score is the same as before what was the what I call the predicted hypothesis. That's the same. But you can define hope and fear also in different ways, and it leads to different algorithms, and actually you can combine almost whatever hope with whatever fear hypothesis, so you have a number of algorithms resulting from this. So what's the idea of cost diminish hope? So originally we had here only the cost, so we were looking only for the hope hypothesis with a minimal number of errors. But here I also want to choose such hypothesis which is scored by my system highly or reasonably. So take some compromise between the score and the cost. The reason or the motivation for this may be really the best hypothesis, even if it is reachable. It has very low score from my system. And when I choose this for boosting, I would still never be able to, well, to promote it enough. If I have aggressive updates without the constraint C, then I would do it, but I would change the weights too much, which I don't want. So this is somehow reasonable compromise. And similarly for the fear, before you took just the hypothesis with maximal score from your prediction model. But you can also add the cost, a number of errors, which means the fear, what I fear most, it's a hypothesis which has both high score from my model, so it's probable that it will be predicted, but it will do most harm for me. Many errors will came from this. And also, I can select the fear hypothesis only based on the cost. So the hypothesis which will cause the most errors, this will be the fear. So here is an illustration from, actually this is the NBEST list from machine translation, and this axis, it's minus cost. So if you are used to blue score, you can imagine a blue score here. So the higher the hypothesis is here, or the translation, the better it is objectively. I take the blue score here as the objective metric. So this is the really best translation possible. And here is the score of my model. So this is the Y-pred, the prediction I would do. And, well, I don't have the illustration here, but what I can do when I do the cost diminished and cost augmented selection of hope and fear is that instead of having a vertical line here and horizontal, I take this, and maybe this will be the hypothesis which I fear the most. So it has both quite high score, but many errors. It's a wrong translation. And similarly, maybe this is really the best translation, but I'm not able to actually, my system, there is a too big difference between this. So it will be better to boost maybe this hypothesis. And the motivation is, since it's online prediction, I may get the same sentence another time or maybe a similar sentence. So maybe next time, this hypothesis will be the best, the hypothesis with the maximum score, but maybe this hypothesis next time will be my hope. So sometimes this is called ramp loss. So it's somehow trying to guide your algorithm in a good way. So it's a nice trick, and the reason why I put this into my presentation is that the last part about when we are going back to machine translation, I'm really excited about this, but I'm not sure if it will actually work. But this is proved techniques, and I hope many of you can use it, exploit it. It's quite simple. When you have to implement support vector machines, it's too hard, but implement online algorithms like this, it's quite easy, and you need to do it for different problems, you must adapt it. So I think it's useful to know just that it exists. Okay, and I've already mentioned some of the problems when applying this to machine translation. So X is the whole source sentence, this is the reference translation. The problems we have. First, we may have more reference translations available, so we don't know which one is the gold or hope. Well, this is not the worst problem. Worst problem is that the reference may be not reachable. And actually, we score derivations. The features are computed from the derivation. We need to know how it was segmented. When we only know the translation, we don't know which features were there. So if the reference is not reachable, and we cannot use the reference hypothesis as the hope, because we don't know, we don't have any features for this. So actually, if you ask why are here such stripes, these are hypotheses which have exactly the same blue score. And either it may be that two different translations have the same blue score, it's possible, but also these may be the different derivations of the same translation. So, okay. And now guided learning, we are going deeper and deeper, so we will start easily first. So, easy first decoding was invented or first published in 2007 here in Prague, ACL, by Shen and Arvind Joshi, and it was originally used for part of speech tagging. So the idea is you have a sequence of words on the input, and these are the possible tags. Well, maybe you have all possible tags for each word, or you have pruned it from dictionary. I was just lazy to draw there too many circles. And this is the score. Now the score is on this axis, unlike on the previous slide. So well, first, how does usual HMM decoding work is that you go from left to right. You decode a sentence from left to right. You have Viterbi search, or sometimes a beam search if it's too broad, and you try all the hypotheses, but you grow it from left to right. The idea of easy first, or sometimes called non-direction decoding, is let's start with the word where we are most confident. So here it is the noun for book. It had the highest score. The score, it's a structured prediction, but here is computed on neighboring words. Maybe here it was just a bigram models, so we can look on we can look on all words, and the features are computed also based on previous tag, and here we can also look on the following tag. It was not possible in HMM, but it is possible here. So, but now no tags were assigned, so just without knowing any neighboring tags, this get the highest score. So we fix it. Okay, we have tagged the book as noun. Therefore, we just delete the other hypothesis here. And now, what happened here? Here was the hypothesis that that is a determiner, and it had a lower score than hypothesis that it's a conjunction subordinate. So, but now there was a feature which says if the current tag is determiner and the following tag is noun, then this feature is 1, and probably this feature had high weight, so it boosted, promoted this hypothesis up. So, similarly, another hypothesis that can be also adverb, that large something. So, it's not so probable that adverb is before noun, let's say, or actually this feature is 1, and when it went down, it means it had a negative weight. So this way, other hypotheses can be rescored based on the part we have already annotated. So the next score is here, adjective, now here determiner, okay. And what about now? Well, maybe the determiner boosted both of these hypotheses, but still the wrong tag got a higher score. So if we are in the decoding phase, in the real tagging on test data, then we don't know that it's wrong, so we just apply it here and continue. So now we are switching to even more interesting question, how to train such an easy first decoder or tagger. Well, you could train it just by extracting relative frequencies or whatever, and it would work somehow. Actually, even before this year, there were such easy first decoders which were not trained using this approach, which is called guided learning. So the idea of guided learning is that you simulate the decoding or tagging in this case in the learning phase. So we have done all the previous steps as I showed before, and no error was done, and we are applying here online learning, so no update was done to the weights. But here an error would be done, so this is our fear, and the original algorithm from of guided learning says that the hope will be the idea in the same stack for the same word, and actually there can be only one correct tag in for each word, so it's uniquely defined. Well, maybe you can ask, why haven't they chosen this for hope? Could it be possible or not? Well, I'm not sure if it's reasonable for part of speech tagging. Maybe it's only this gives the best results. I think they didn't try to choose another another hypothesis as a fear or as a hope. But I will show that it's not so easy when, or not so, easy to decide when we move to other problems. And of course, my goal is machine translation. But first, I will just quickly show that easy first decoding was used for dependency parsing. By the way, this guided learning tagger was state of the art in 2007, and Easy First Decoder was also for some time state of the art. So the idea is similar. I will just show the animation. So here the hypothesis for each word is actually, you have just two hypotheses possible. Attach the word to the left or right word. And for each such action, you have a score. And you can see this is the highest score. So you will select the hypothesis with highest score, and brown was attached below fox. And now, what's the highest score? Probably this one. So I will attach it here, and so on. So here is the rest of the steps. And the Easy First Decoder for parsing is also trained using guided learning. And even newer implementation than this, which adds some new features, is called FANCE parser, fast and accurate parser, by a student at HUVI, Stephen Trutz. And if you're interested, it's implemented in Trees, although it needs to be retrained. So I have just few minutes. So back to machine translation. How to do Easy First decoding. Now, the problem here is that the segments are overlapping. I selected for simplicity phrase-based machine translation, although my goal is 3-to-3 translation and tectogrammatical, but this is easier to draw on a slide. And I selected just bigrams of just phrases of maximum length 2. So for each segment or source phrase, you have a hypothesis. So here we can see that the highest hypothesis is just to translate book as kniha, but you have also a hypothesis which translate book interesting as kniha zajímavá. So this is the highest hypothesis. Let's select it. We delete the hypotheses which are not compatible with the selected hypothesis. So, of course, this one, but also this one, since it's overlapping, and it would translate book as rezervovat. So it's not compatible with kniha. But this hypothesis stays here, and also this hypothesis. It's not correct hypothesis, but it's not in conflict with the selected one. And now what's interesting here, we can use the language model. So we have translated this word book, and it's neighboring with interesting. So the translations of interesting, their translation will be changed their score. So probably book is feminine, so this word will be boosted and this penalized. So now this one is the highest scoring hypothesis, so we select this. And since we have selected this word and this word, then also this is implicitly translated. No incorrect hypothesis could be left there. Well, and now the problem is this. Error would happen here in decoding. So what to do in training? Well, probably this seems reasonable to select as the fear hypothesis. But what should be selected as hope? Should we hope? Well, actually, there is no correct translation for found dead available. It was not extracted from the data. So should we try to, maybe if we boost this translation up, so it will be not compatible with this, so this translation, this hypothesis will be deleted and we will win. But it's too long margin. Maybe let's promote this one. And maybe we can somehow travel. Actually, we are building isles of correctly translated, hopefully correctly translated words, and using the language model and also the compatibility with already translated sentences, maybe we can get rid of this fear translation. So that's what I'm working on. I have some prototype, but on only small data. I want to learn what's going on inside, how to get the language model inside. So this is work in progress. Actually, the features you can use can be divided into features which, where you look only on the source segment. So you can look how large the segment was. What was the entropy for all possible translations for this segment, but you don't look on a particular translation. You just take them all. So probably I would guess that segments with lower entropy, where you are more sure what should be the correct translation, should be translated first. And the source language model, I don't know whether it's reasonable to put it there, how many times you have seen this source segment. You can look on the identity of the segment, so maybe found that is not a good segment to be translated at all, although the probabilities, the relative frequencies are high. Maybe you want to look on the part of speech text. The division into those two features gives some insights how to select the fear and hope. You know that when you change only the segment wise features, then you would either boost all of those hypotheses or penalize them. But you cannot change their order. This part of the score is shared by all of them. So if you decide to choose a hope hypothesis from here, if it was here, then you probably should look whether it's reasonable from the target dependence features. So this is the probability of the translation model. Actually, it's logarithm, so it's scaled, but maybe you can also do another functions from this. And finally, you can get combinations of more features and quantizations. So I'm sorry this was too fast, but hopefully I will tell you more sometimes later, or if you have questions now. But I will just show how to apply it to tectogrammatical trees. So we have just lemmas and phonemes, and to make it simpler, I decided that I will transform the tree so each node is divided into two. The upper is the phoneme and the lower is the lemma. And the advantage is first that it's simpler to implement. You have just one label for each node. And also, it has some linguistic motivation that a phoneme is actually kind of a label of the edge, usually. Or you can try to think of some counter examples where there would be dependency, I mean more statistical, but it's kind of maybe also linguistical. For example, between those two words, but not the phoneme. Well, but I think it's a good factorization that I want to take only tree-led, so connected subgraphs of it's such tree as the segments. So, as a summary, what we have seen in our zoo, some real animals, some myths, and some really strange chimeras. I tried to show you how easy it is to be passive-aggressive. And the guided learning. And finally, for future, what are your predictions into the future? Well, it's a quiz. What do you think this is? I didn't have any questions so far, so no answer. No, it's not. So actually, it's from Google Ngrams and Czech corpus, how frequent was the word hope and fear and their translation in Czech in all books. So, I don't know, lucky times were some in the half of the century. Now there is more fear than before. In English, there is still more hope, but you can see this boosting. Maybe it is because of structured prediction, I think. So let's try to do structured prediction as well. Okay, thank you for your attention.
Thank you very much for your interesting guidance through the zoo. And I now open the floor for questions. So I will just start one question for clarification. When you spoke about the guided, the features for the guided model, I don't know whether I have not overheard something, but you said that you don't, or you were just not very sure whether you should use the features for the language model for the source of the source, and I somehow heard a question mark.
Yes.
And I just wonder why.
Well, I haven't tried this yet, and the motivation would be, well, usually in machine translation you use the language model of the target language, so you want to produce smooth translations. Here it is just, I want to find which segments are good candidates for being translated. Some segments are frequent enough, but maybe they are hard to translate first, so you want to start with another. And probably, if the segment is not probable, if I think of the treelet, so I think about the tree language model, but it would hold also for the n-gram language model. So if there is an edge which was not seen any before, then the final score of the treelet would be low. And I think if I haven't seen such treelet before, I should not translate it first. Probably also the count of the source will be low in that case, but maybe the entropy will look nice. I have seen it once, and with one translation, so I have 100 probability, so it's entropy of 0. Actually, the entropy will get a negative weight, I hope, and it was proven in the experiment. So this is the motivation for the source language model. It should do something similar as the count, but I don't know.
Well, maybe I'm wrong, but I remember one paper by Martin Kay, I don't know, 20 years ago or something like that, when he proposed, or where he said that it might be good to have a system. Well, he spoke there about the possibility to think of some kind of pivot language, so the vocal triangle. And he said that what he can imagine, but had no concrete proposal, would be some kind of negotiation between the source and target. So somehow when the target, that you feel you don't know how to go on in target, the target part can negotiate with the source part and find some preferences or some solutions. So this is why I asked you the question, because I somehow feel there might be a kind of analogy with...
Thank you for suggesting. It's a different motivation, but yes. Sometimes it's also you try to translate the sentence there and back, and you get some confidence score without reference translation, and it can be used if you have a setting where you need to translate, let's say, 50 sentences out of 100, and you can choose which one, then you can use such trick, and there the language model source could be also used.
So, further questions?
So thanks for a very dense, filling hamburger. I was wondering if it's easy to extend the easy first decoding to, well, beyond sequence labeling, because basically what you're doing is kind of sequence labeling task, but the decoding that we do in phrase-based is, well, I don't know. It always seems more like complicated. Could you adapt phrase-based? Now the slide says phrase-based MD. So.
Well, it's a very good question. I think it's not only limited to sequence labeling. Actually, I've seen applied for dependency parsing. And what I do, I translate treelets, and here it was isomorphic, one word to one word. But I want to allow also non-isomorphic treelets where I can change the topology or even the number of nodes in the rule. I have not implemented it yet, but it should be possible. The problem is different. It can be applied for my TectoMT style of translation of trees, but in a phrase-based system, you actually you need to build the target sentence from left to right in the beam search usually. There were some attempts to change it, but none of them, as I found, was similar to this easy first, so I think I'm the first one to adapt it from other tasks to MT. And the problem is in phrase-based translation, you must do also reordering jointly with the translation. In TectoMT, we can translate the tree, and we can use also the tree language model which doesn't care about the word order, let's say. And afterwards, we can solve the reordering. For Czech, it's quite easy using some rules, but for other languages, it could be statistically learned, but as another step. But if you want to have it joined, then I thought, well, I can say someone from phrase-based, let's use my decoder, but there will be some problems, so it's an open question.
Well, I'm sorry, but there are many people, I suppose, waiting in front of the door to be let in. So I would like to thank you again for your talk. I hope that the discussion can be continued in a kind of private or group-like manner. I just would like to tell you that the next seminar is being prepared by Barbara Hladka and her student. And the last one, I mean, in 2 weeks, Professor Leo Wanner will be here from Barcelona, and I hope he will say something about Melchuk-like annotation of corpus, but you will see it on our web, I mean, the exact program. So thank you again, and see you next week.